Hello, my name is Kelly. Welcome to Angular Momentum Review, aka the second half of Unit 7. Oh yeah, here. This is Koshka. Oh, hello. Alright, let's hop in with some angular momentum. As always, here are our social media links. On Twitter, Instagram, and YouTube, we're at Think5able. Where you can find a lot of fun extra information to help you along your AP Physics journey. Okay, so this stream is Unit 7, Part 2, aka Angular Momentum and How Torque Causes Angular Momentum, and then Conservation of Angular Momentum. One of the big ideas of this unit is that a net torque exerted on a system by other objects or systems is going to change the angular momentum of the system. So just like how in our linear kinematics and linear Newton's second law and whatnot, if you push on something, it's going to cause a change to the momentum, right? So the same thing happens here, where if you torque something, it's going to change the angular momentum. And one of our equations that we can look at with this is this one. So the change in angular momentum, or delta L, is the torque multiplied by the change in time. So a torque exerted on an object for some period of time is going to change the angular momentum of that object. And just like regular momentum, angular momentum is a vector. So last week we talked about how for every linear kinematic equation, there was a rotational analog that went along with that. So every time you saw acceleration in your kinematic equations, you saw angular acceleration in the rotational ones. Velocity had angular velocity. Position had angular position. So the same kind of works here. So anywhere you see regular momentum, or delta P, you get angular momentum, delta L. Anytime you see force, you can replace it with torque. And then time is just time, no matter if you're going in a straight line or in a circle, so that stays the same. So one of the learning goals for this unit is that you can predict the behavior of a rotational collision situation, just like you do with linear collisions, by using the analogy between impulse, which is the delta P equals F delta T for linear momentum, and the delta L equals tau delta T for angular momentum. All right. One of our other relationships for angular momentum is L equals I omega. And this is probably one of the ones you're going to see most often, I would say. So the magnitude of the angular momentum of an extended object is just the moment of inertia multiplied by the angular velocity of that object. One thing to remember is that you do not need to know the equations for an object's rotational inertia. All of those are going to be provided to you on the exam. So don't fret being like, oh my gosh, I can't remember what the moment of inertia for a sphere versus a shell is. They'll give that to you. But you should have a qualitative sense of what factors affect that rotational inertia. So why does a hoop have more inertia than a puck of the same radius and mass? And we're going to get into that a little bit more in depth in a couple of slides. All right, so L equals I omega. Blah, blah. All right, here's our handy dandy chart of all of our moments of inertia. And again, you don't have to remember these. These will all be given to you on your problems. All right, so starting from the top left, we have our solid cylinder or disk rotating about the symmetry axis. So that's if you have your puck and your axis of rotation is in the middle. So like a spinning record, a merry-go-round, things like that. And the inertia is 1/2 mr². where m is the mass and r is the radius of that disk. For a hoop, about the center symmetry axis, so about the, oh my gosh, I can't talk right now. Sorry. So if you're spinning a hoop around the center, the inertia is just mr squared. So like we mentioned on the last slide, your hoop has a greater moment of inertia than your disk does for the same mass and radius. And that's because if the mass is further away from the point of rotation, it's going to be harder to get it to rotate. So the further away from the center the mass is, the higher your moment of inertia. So for your disk, it's spread out all over the entire thing. So it spins pretty easy because there's still some close to the middle. Whereas if all of it's on the outside, it's like, trying to push it harder. Same thing happens for our solid sphere, 2/5 mr squared, versus our thin spherical shell. So like a hollow sphere. 2/5 is smaller than 2/3. So if all of the mass is concentrated to the outside, it has a higher moment of inertia. The rod spinning about the center, so if you take your stick and you just pin it right through the middle, is 1/12 ml squared, where L is the entire length of the stick. And if you pin it at the end instead and then spin it, it's 1/3 ml squared. All right, so now if we have our disk and our puck, but instead of spinning it around the center, we spin it through the length of it. So kind of like, what are those things? Have you ever seen those like illusion things where it has like a picture of like a bird on one side and a picture of a cage on the other with a string through the middle? And you like spin it really fast and you can see the bird in the cage. It's in that one movie, like The Illusionist, I think. I don't remember, but that's what we're talking about. We're talking about like the disk with the axis of rotation pinning it through this way. So the moment of inertia for a solid one is 1/4 mr squared plus 1/12 ml squared, which is the length of the cylinder or the thickness of the disk. And for a hoop, it's just 1/2 mr squared. Woo. Okay. So the rotational inertia of an object or system depends on the distribution of mass within the object or system. So if you change the radius of an object or a system, or if you change the distribution of mass within the system, it's going to change the rotational inertia. And therefore, it's going to change the angular velocity and linear speed for a given angular momentum. And you should have a qualitative understanding that your rotational inertia is larger when the mass is farther from the axis of rotation. So if you can remember nothing else, remember the ice skater. If I can get it to play for you. Ah! Play. Maybe not. Played myself. Da-na-na-na-na. Ha-ha. Okay. All right. So you guys are all familiar with like the ice skater spinning on the ice. When they have their limbs out, they're spinning pretty slow. But when they suck their limbs in really close, they start spinning a lot faster. That's because they're bringing their mass closer to the axis of rotation, so they're decreasing their inertia and therefore increasing their angular momentum. Or their angular momentum stays the same, so they decrease their inertia, so their angular velocity has to increase to make up for it. Conservation of angular momentum. Woo! Okay. So we have a quick question. I'm going to pop that into the poll so you can answer it. So we have two identical cars, blah, 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 are racing around the track. Impossible to tell. they are the same. The inside one and the outside one. Okay. Can you see that? All right, so two identical cars racing around a track. Which one has the greater moment of inertia? We have one vote. There are two of you. I can see. Perfect. Okay. Yeah, so the outside one has the greater moment of inertia, and therefore the greater angular momentum, because it's further away from the center of the track. Therefore, greater inertia, greater angular momentum. Excellent. All right. Ding. The outside car. Good job. Okay, so now we're going to do a little bit of a calculation problem. We have a merry-go-round. I started pushing a merry-go-round with a torque of 10 Newton meters. It has a moment of inertia of 100 kilogram meters squared. What is its rotational speed after 3 seconds, assuming it starts from rest? Okay, so we have our merry-go-round. We know that our torque is 10 Newton meters. So torque is 10 Newton meters. We also know that it has a moment of inertia of 100 kilogram meters squared. So I equals 100 kilograms times meters squared. What is its rotational speed after 3 seconds, assuming it starts at rest? So our change in time is 3 seconds, and we start from rest. So angular speed is radians per second, or just inverse seconds, because most people don't put radians in their units. Okay, so we're going to use our relationship that our change in angular momentum is equal to the torque times delta t. So we know the torque, we know the time, so we can get our angular momentum. And then from there, we know that our angular momentum is related to our angular speed by L equals I omega. So since we start from rest, our initial angular momentum is 0. So remember, change is final minus initial, right? So L final minus L initial. Well, we start from rest, so that's 0. Is equal to torque, delta T. Final minus initial, and delta T, we can always just say is 3 seconds because we assume we start at 0. Okay, so I'm going to take that. I like to leave everything algebraic until the very end. So my angular momentum is torque delta T is equal to I omega final. So omega final is torque delta T divided by my moment of inertia. So that's 10 newtons times meters. Delta T was 3 seconds. And my moment of inertia was 100 kilograms times meters squared. All right. So one of my meters goes away. Remember that a Newton is a kilogram meter per second squared. So my other meter goes away. My kilograms go away. One of my seconds goes away. And I'm left with 0.3 inverse seconds. So radians per second. So this is one of those where they're going to try to trick you on your multiple choice answers. Don't fall for it with the units. So not that it matters to you now because you don't have multiple choice on your exam, but one of the ways that the AP exam likes to trick you is by putting in different units. And that's what they did in this question by putting in 0.3 seconds and 0.3 inverse seconds. So if you ever get stuck on a multiple choice problem, always make sure the units are what they're supposed to be. Alrighty. Give you 2 more seconds, just in case you're taking notes. And then we're gonna pop back over. Do 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 do. All right. Hello again from the close-up of my face. Okay. All right, so the answer is D, 0.3 inverse seconds, aka radians per second. Not to be confused with C, 0.3 seconds. Okay, next thing that we have is that the angular momentum of a point object, let me blow this back up, is given by L equals mvr, where mv is our linear momentum and r is the distance from that point to the axis of rotation. Now, if you can't remember this, that's okay, because you can derive it from L equals I omega. So the moment of inertia of a point is mr squared, where r is the distance from the point to the axis of rotation. Omega is the linear velocity over r. So from L equals I omega, we get mr squared, v over r, which simplifies to mvr. So if you can't remember the angular momentum of a point, that's okay. You can derive it from all your other equations as well. Oh, am I? Hello. Can you hear me? Can you hear me now? Is that better? Uh-oh. Okay, cool. Sweet. I hope I haven't been talking to myself this entire time. So no worries. All right. So also, in case you guys didn't know, this will be posted on the Fiveable website after the stream. So if you're part of the what is it, the Cram Pass or whatever, I think you can see all the videos after the fact. Okay. Okay. Where are we? All right. So if you can't remember what your angular momentum of a point object is, you can always get it back again from L equals I omega, and the inertia of a point is just mr squared. Okay. One of the other things, so torque, angular momentum, angular velocity, and angular acceleration are all vectors, right? So when you have a vector, you need to know what direction that vector points. So in order to do that for our angular momentum and also for angular velocity, we use our handy dandy right-hand rule. So there's 2 right-hand rules in physics. The second one, I don't think you're going to learn. Well, You'll probably still learn it in class, but it's not going to be on your exam. And that's for electricity and magnetism. That's like what we call the physics gang sign, if you will. But the easy one that I like to show for rotational stuff is the squirrely thumb one. So if you take your right hand, you give a nice thumbs up, you point your finger, your thumb is in the direction of the vector, your angular momentum, and your fingers curl the direction that you're spinning. So if I have something spinning this way, the direction of my angular velocity vector and also my angular momentum vector is thumbs out towards me. It's weird. But that is the most you will ever have to even think about right-hand rules on your exam. Plus, you probably actually won't need to know it. I just like to tell it to you. So you're like, is this in the same direction or the other direction? All right. Our next super, super duper important enduring understanding is that the angular momentum of a system is conserved. So just like in our linear momentum cases, when we're crashing cars into each other, momentum is conserved. And that's how we solve the vast majority of our angular momentum problems, is taking advantage of that fact. So what better way to do that than with a question? We're going to pop this into a poll because I like them. Okay. It is halved. Ordered. I can spell today. It remains the same. It is the bulb. It is quadrupled. Blank. Okay. So in an isolated system, the moment of inertia of a rotating object is halved. What happens to the angular velocity of the object? Okie dokie. Good job. All right, so angular momentum is conserved in an isolated system. So if L stays the same, if I goes down by a factor of 2, then omega has to go up by a factor of 2 to compensate. That's from our L equals I omega. Good job, team. Good job. All right. Next super duper important thing that they emphasize you need to know is that the angular momentum of a system with respect to an axis of rotation is the sum of the angular momenta with respect to that axis of the objects that make up the system. So if you have more than one thing spinning around in a circle, you just add them all up separate. All right, which we're going to put in equation form right now. Blah. All right. So the angular momentum of a system is determined by the locations and the velocities of those objects. So if we're talking about points, on the bottom, we have the angular momentum of a point is mvr. So if you have more than one point mass, you just add up all the mvrs based on where you're rotating around. So you can do the same with inertia, and you can do the same with angular momentum. You just calculate them individually based on their individual distances from the axis of rotation, and then add them all up. Okay. So you need to be able to describe or calculate the angular momentum and rotational inertia of a system in terms of the locations and velocities of the objects that make up that system. And you also need to use qualitative reasoning with compound objects and perform calculations with a fixed set of extended objects and point masses that make up the system. So here's an example of what they're asking you to do. This is a system where we have a blob of clay dropped on top of a rotating disk. So our system is the disk and the blob of clay. So a blob of clay of mass m is dropped on top of a rotating disk's edge of mass 2m, spinning at a speed of omega naught. What will the resulting rotational speed omega be? Okay. We're going to create a poll because I like them. The first answer is a quarter, half, 1, 2, 4. Quarter, omega naught. A half, omega naught. Omega naught. 2, omega. All right, so I'll give you guys a couple minutes to do this one, then we'll head on over to the whiteboard. Which I'm going to go erase. Okay. Everybody's in. To the whiteboard we go. And the process it takes to get there. To the Chrome tabs, that is the whiteboard. And then we're gonna go back and focus. Okay. Alrighty. So in our handy dandy problem, we start out with a disk shoop, spinning around, we'll say this way, at an angular speed of omega naught. And our disk has a mass of 2m. 2m. And then, that's the worst disk I've ever drawn in my entire life. Cool. We take a blob. Yes. Beautiful blob of mass m, and we slap it on there at the edge. And we want to know, what will the resulting rotational speed omega be? Okay. So whenever I do collision type problems, whether it be with linear or with angular. I like to think of it as like initial equals final for our conservation. So initially, the angular momentum of this thing is equal to I omega. So I have a disk. The inertia, the rotational inertia, wow. The rotational inertia of a disk is 1/2 mr squared. So 1/2. The mass of this guy, however, is 2m r squared and omega naught. So my 2's cancel out. I get my m r squared omega naught. At the end, these things are stuck together, so they're going to be going at the same angular velocity. So I have my disk, which is my 1/2 m r squared, plus my blob, which is m r squared omega final. The 2's cancel here. So I have mr squared plus mr squared times omega. So 2 mr squared omega. Cool. So now I set my initial equal to my final. Mr squared omega naught is equal to 2 mr squared omega final. My m's cancel, yay. My r squareds cancel, yay. And omega naught is 2 omega, but that's not what we want. We want omega. So we divide that 2 to the other side to get omega is 1/2 omega naught. Easy peasy, lemon squeezy. Okay. So we start off with our satellite rotating once per minute. So initial. So that is telling us information about our angular speed. So it's rotating, so 1 rotation per minute. Okay. Then we know that it has a moment of inertia of 10,000 kilogram meters squared. (10,000 kilogram meters squared). And after they stick out the little legs, the solar panels of the satellite, moment of inertia increases to 30,000. Okay. So moment of inertia goes to 30,000 kilogram meters squared. And we want to know what is the final angular velocity. Okay. All right, so we know that angular momentum is equal to I omega. All right, so omega we need to turn into radians per second, but we don't really have to because we could also just look at it in the units that it's in. So our L initial is 10,000 kilogram meters squared times omega, 1 rotation per 1 minute. is equal to final 30,000 kilogram meters squared times omega. Okay. So if we divide this side by 30,000 kilogram meters squared, 30,000 kilogram meters squared. All right, so kilograms and the meter squareds go away, so we're left with units of rotations per minute. Sweet. My zeros go away, blah, blah, blah. So we get 1 rotation every 3 minutes. Wow, that was a hideous box. Cooley up. All right. Let's try another one. Okay. Okay. We are going to upload a file to here. Great. Okay. Can you see that? Dang it, that didn't work. Okay, never mind. We're not going to do that. All right. We're going to pick a different one then. All right. Dun, 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 dun. Dun, 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 dun. Whoa. This is a terrible, terrible whiteboard. Okay, we're just going to go back and put it in the poll like we were doing. That's fine. Okay. Okay, so we have a comet orbiting a star in a far distant galaxy with only gravity acting upon it. I'm going to add in all my answers. And 2. Okay. All right, so a comet is orbiting a star in a far distant galaxy with only gravity acting upon it. After a period of time, the sun's radiation partially melts the comet, decreasing the mass to 1/4 of what it was. Simultaneously, because of an irregular orbit, its distance to the star doubles. What expression best describes the comet's angular velocity v compared to its original conditions before the melting and distance change? All right, to the whiteboard. Okay. So we know that we have a comet orbiting Far, far away, with only gravity acting upon it. Okay. So because there are no outside forces except for the gravity that's making it go in the orbit in the first place, angular momentum is going to be conserved. Right? So L initial is equal to L final. Now this comet is more or less a point orbiting around space. So the angular momentum of that is mvr. Remember where this is our linear momentum, which we get from I omega, which is mr squared v over r, mvr. Okay? So initially, our comet is just cruising around, and then the sun partially melts the comet, decreasing the mass to a fourth of what it was. So if our initial angular momentum was mvr, then our final angular momentum, m, decreases by a factor of 4. Simultaneously, because of its irregular orbit, the distance to the star doubles. So our r becomes 2r. What happens to the velocity? All right, so if we simplify this down, my 2 can cancel out one of those. So now we have mv naught r is equal to 1/2 mv final r. My m's go away, my r's go away. So my initial velocity is 1/2 of my final velocity. So my final velocity is 2 times my initial velocity. So these are the kinds of questions that they can throw at you for basically any topic. You see these a lot in circuits, which aren't going to be on your test, so I don't know why I said that. But you see it a lot. You can see it a lot in circular motion, in kinematics and energy conservation, those kinds of things. They'll be like, okay, what happens to this quantity if you double this or you decrease this by a factor of 2? So the way that I like to approach those is set the initial values as like the variable. So like here we said, okay, initially we started with the mass m, and then we decrease it by a factor of 4. So in the next one, I'm going to plug in m over 4 so that you can write it in terms of the thing that you start with. And just like our distance doubles, so instead of r, it's 2r. And then you can set those things equal to each other and see how it changes the remaining variables. But yeah. Okay. So next week, I'm going to get extra questions ahead of time. Sorry, y'all. Yeah, do you have any leftover questions about angular momentum before we sign off for the review next time? Or do you have anything specifically for units 1 through 4 that you want to cover next week? That's going to be our kinematics, energy, and forces. I think it's those 4 things. And circular motion. Like gravitational circular motion, like orbits and stuff. Cool. Coolio. So I'll hang out for the next 5 minutes. If something pops into your head for either right now or for next week so I can make sure that it goes in. And yeah, have a good night. Hope all is well. Try not to go crazy inside your house. Hang in there. You're doing great. Oh yeah, my pleasure. This is my second stream ever, so I haven't quite figured out the timing yet. So thanks for being here. Hope to see you next time, where I will have extra questions. Boo, 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 doo, doo. Alrighty. Just gonna X that out. And then, so Allie, you're the only one here. Do you have any burning angular momentum questions? Are you good? Hanging out? Want to see some sleepy cats? I kid, I kid. Cool. Good talk. Alright, I'll see you next week. Hopefully. Stop on by. Don't forget to show up to Peter's free response question practice at 1 o'clock on Wednesdays, because he's going over the types of questions you're going to encounter on your exam, which is very, 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 very important to do. Because they like to throw you curveballs, and they also like to reuse things too. Okie dokie, have a good night.